Now that we know what lists are and how they're represented, let's show how to do calculations with lists. So first I want to show you how to construct a list piece by piece. So for example, I will have the list x1 equal to 6 bar x2. Now I have to be careful because the declare instruction will declare new variables for all the identifiers that are on the left-hand side of the equal. But in fact, that's not enough here. I also want to declare a variable for x2. So there's a variation of the declare where I can put all the identifiers that need to be redeclared up front, followed by in. So I do declare x1, x2 in, and then the instruction that comes after, nothing is redeclared in there. So there, now I will declare x1 and x2. So I feed region. See, if I now do a browse of x1, I will see 6 bar underscore. So notice the underscore represents the unbound variable. If I now continue, I say, for example, x2 is equal to 7 bar x3. Again, I have to be careful. I don't want to redeclare x2, but I do want to declare x3. So again, I use the variation of declare, where all the redeclared variables are put up front. Here I will only do x3. So again, I feed this. Notice that the browser updates the display to 6 bar 7 bar underscore. So the browser is able to update the binding of single assignment variables. Finally, let me do x3 is equal to nil. And here the list now is complete. It's now 6 bar 7 bar nil. If I now do a browse of x1, the original list, 6, 7, nil, since the browser knows that it's actually a complete list, it's able to use the bracket notation. But these two are exactly the same. And I can verify that. For example, if I do browse 6, 7, bracket notation equal 6 bar 7 bar nil. If I execute this, it says true. Remember, the bracket notation is a syntactic sugar. Let me now show some built-in functions for lists. So the built-in functions will be the .1 and the .2 functions. The .1 gives you what's on the left-hand side of the bar, and the .2 which is on the right-hand side of the bar. So it only works for non-empty lists. It does not work for nil. So for example, remember I do browse of x1. This gives 6, 7. If I do browse of x1.1, this gives me the left-hand side of the bar. Remember that this is actually the list 6 bar 7 bar nil, which is the list 6 bar followed by another list. So the bar 1 will display 6. Here, 6 is displayed. And there's the complementary function .2, the .2 function, which displays the list on the right-hand side. So the first element for .1 and the rest of the list for .2. In many languages, this is called the head of the list. In Lisp, it's usually called the car of a list. And the .2 is called the tail of the list. And the Lisp is called the cdr of a list, CDR. So, but we will use the .1 and .2 notation, which will have good reason later to see why it's like that. So let me now ask you, what would I have to write if I want to see a 7 displayed, the second element of the list? So pause the video, maybe if you want, think a little bit. So what I have to do first is take the rest of the list and then the first element. So it's .2, .1. And this will display 7. Okay? Now, that's a recursive function, a built-in function. Now let's define a recursive function on a list. Let's define sum of elements of a list of integers. Okay? Sum L is the list argument, using the .1 and the .2. So if L is equal to nil, empty list, then 0, the sum is 0. Otherwise, it's L.1 plus sum of L.2. So you see, using the .1 and the .2 functions, it's very easy to write functions, recursive functions using lists. Let me define this. Let me now execute this using our list x1, which gives me 13, 6 plus 7. Now, notice that this is a recursive function following the recursive structure of the list. It's a very important insight. Recursive function and recursive data types fit together very well. And now I'm going to show you something neat. Notice that the sum that I just defined is not tail recursive. So let me define a tail recursive sum. This one needs an accumulator. Let me call this one sum2. It needs an accumulator, a, and so I will have to accumulate the result. So if L is equal to nil, then a, else, notice sum2 is going to be the final operation. I have L.2 and L.1 plus a. There we go. So let me execute this. Sum2, if I want to call it on x1, I have to give an initial value of the accumulator, which is 0, and this also shows 13. Okay, so what is the invariant for this? This one was fairly easy, so I didn't have to write down the invariant explicitly. But what is the invariant for this? Remember, invariant is a formula that will have to have L and A in it. Let me give another example. Nth element of a list, of a different kind of recursive function of a list. Notice a list is defined recursively as an element followed by another list. So there is no direct access to the nth element. The only way is to traverse the list down recursively until we find the nth element. So in order to define the function nth, so we have a list and we want the nth element, we need to do a recursion, but not on L, on n. So if n is equal to 1, then the first element is L.1. Otherwise, we have to go down the list, so we go L.2, and we do n minus 1, because we're one element farther. Okay? So let me define this. Let me show you then nth of x1, the second element, which is going to be 7. So this is recursing not on the list's recursive definition, but on the integer, n. Now, what happens if I call it with a list of 2 elements and I want the 5th element? What will it do?